All right. Hello, everybody. My name's Nick Rutan. I was doing this lab with Dakota Harmon, and I think we did this lab on around March 5th and March 7th before everything got shut down, obviously. So for our lab, what we did, we estimated the specific heat of air. To do this, it took a wide variety of processes, a lot of math, a lot of differential equation solving, sort of, but they gave us the road work so that we could figure it out. But fortunately, let me see if I can figure out how to go to the next slide. There we go. Okay. And in this talk, normally I would start with the theory aspects of this, but since it's pretty abstract with the derivations that we use, I wanted to show the experimental setup first and saw how with our oscillating of a ball above a tube that we can come up with the equations and solving them to be able to solve for the specific heat of air and the kappa value, which I'll explain here in a minute. But first of all, we're going to go through the experimental setup theory, show the data analysis and the error analysis that we had. The errors were very, I don't know, there were a lot of possible sources of error in this experiment, and I'm actually pretty proud of how accurate our numbers really were when we account for all the possibilities of error that we could have had. And then we'll wrap that up with the conclusion there at the end. So here's our experimental setup to a degree. I tried to get a video of one of the many that we had to record to be able to do this, but for some reason, every time I tried to install that into this PowerPoint, it crashed PowerPoint over and over, and I couldn't figure it out. But here's the basic setup: is that we have this volume of air, and that's our blue casing tube at the bottom. And there we have this smaller skinny tube that sticks out of it, out the top. And we place a metallic ball up at the top. And then when we drop that in with any volume of air inside that jug that we had, the ball would oscillate with a certain frequency. And we can measure that at all these different volumes. And we did it at around 9 values, I think. But to do this, we had to record this ball oscillating above this tube back and forth. And when we recorded that video, we were able to use the tracker app on one of the school computers to measure the displacement of the ball over time. And that way we can record the average period of the ball as it oscillates. And since this ball inside that tube acts as a harmonic oscillator, we are able to use the differential equations and able to solve for the specific heat of air with all these other equations I'm about to show you. All right. So here's how this theory starts. It's pretty abstract and it's pretty complicated. First of all, we know that in an adiabatic system, which means there's no heat added or taken away, the relationship between pressure and volume is related by this PV to the K is equals a constant, okay? And we can usually relate that into like an initial and a final state. But for this case, for diatomic ideal gas, that's our Cp over Cv value. And Cp is the heat capacity of any material. In this case, we're talking about air, so I'll just continue to use air. The Cp of air at constant pressure, that's what the P means, is the heat capacity of air at constant pressure. And then the Cv value is the heat capacity of air at a constant volume. And that ratio for diatomic gas is going to be 1.4 or 7/5, which isn't really important for what we're doing. So in this tube we were talking about, as we drop that ball, we can talk about the forces. So we have our F equals ma, right? And if we go back to this last slide, as this ball drops down that tube, the force acting up on it is related by our area, by our change in pressure. And that's what that AdP equals ma is. And that next equation, the AdP, is basically the acceleration. I think everybody who's taken, I don't know, introductory physics knows that acceleration is the second derivative of position. And that's just basically rewriting that in that next one with that md squared x over dt squared. That's that. And then this next part is, we were actually given this equation because I'm not exactly sure how we're able to even solve for this, but our dp value, That's going to be our negative kappa P over V dV. And so using that equation, we can talk about our differential equation on the next page, but we need that. That's absolutely necessary and able to solve for this kappa value. And then obviously dV, that's our change of volume. That's going to be our area like of the tube that we talked about with that metal ball that drops down. And then that's going to be multiplied by our X value, our position as it oscillates through the tube. That's pretty simple. But this next part's a little bit more complicated. There's some differential equation work and a lot of, I don't know, hand-waving arguments, I suppose, as opposed to doing all the math. But once we plug in all our values for this part here, we can see, if we go back, that this differential equation, this part right here, once we plug in for our dP here, then once we plug in all this stuff, basically, we get this differential equation with what we have here. And since this is a second order differential equation with no damping, it's going to act as a harmonic oscillator, which is perfect. That's what we want. Since we know that ball is going to be oscillating, we can account for our angular frequency. And that's what this value is here. So with this value, if we can calculate what our period of the ball as it oscillates, which is what we did with that tracker app, and we'll show the data on the next page, we're able to show and find what this kappa value is, doing some, I don't know, mental gymnastics with this differential equation here. So we know that from our differential equation here, we're able to show that our angular momentum, or our angular frequency, my fault, is equal to the square root of kappa PA squared over MV. And then we also know, basically from any, I don't know, any period type math that you've ever done, that our period is going to be equal to that 2 pi over that omega value, our angular frequency. And then once we have all that, we basically just plug in our stuff here with our period, because that's one of our measurables. Our pressure is our measurable, our area, volume, mass of the ball, all that we already know. So we can put our kappa in terms of all these values that we already know. So like our mass of the ball, our volume, our area of the tube, our pressure, and our period. So all those things are measurables, and we can solve for kappa that way with this experiment. All right, on to the next page. So here's our data that we're able to get from this. We know that we want that 1.4 value, and using this tracker app, here's one of our graphs basically. So each one of these points is like a tiny increment of time as I track the position of the ball as it oscillates in that tube. And obviously you can see that it's oscillating. So we know that it's going to act in that way. And as we do this, we can find the period basically from doing peak to peak or any middle point that we want, but we use peak to peak to get the average period, because if we only measured one period, it could be really inaccurate. So we tried to do it as many periods as possible. So for this volume of air, for this graph that I plugged in, it's just one of the many that we had that 3.5 liters. And we show that it oscillates. And then for our average period for this 3.5, we had that 0.705 seconds for an average period over that time. So using our equation from that last page, remember, so we had our pressure. So the way that we had our pressure is that we had to use this formula from this last page. Okay, well, basically our pressure is that we wanted the gauge pressure of the system. And to get the gauge pressure of the system, we had to have our P naught pressure, which is our atmospheric pressure. And for Grand Junction, I think that's about 86,000 pascals. And then we had to add our mass times the gravity, so that's our force over our area, to get the gauge pressure within that tube. So to get that, we calculate our pressure, and what our pressure was, I have it here, is that it came out to be about 87,685 pascals. So that's another value we just had to plug into the same formula, if you recall this period here. So then our period for each one I have on the next page. The mass of the ball was actually 0.175 kilograms. So really light. Obviously, it's just like 17 grams or something. All right, I think I said that wrong, but 0.00175, whatever. And then just using this, we were able to solve for our kappa value. And obviously our values aren't too accurate, especially with the smaller volumes of air, and I'll talk about that in a little. That's a little of an interesting find there. But here we get like a 1.22 all the way down. You can read them all, obviously, 1.269, 1.3, all the way down to 1.4 and 5. And that's our most accurate values with the largest volume of air that we're measuring within the tube and within that jug underneath. That's what we care about. So obviously we get, if you pay attention, we get that 1.22 all the way down to the 1.4. We get more accurate as we add the volume of air. And I thought that was pretty interesting. Next, the sources of error that we had, there, like I said before, we had quite a few and it was a little odd. So when we're talking about our DK, so obviously any kind of measuring uncertainties, we have to take in the many possible sources of error. So here, there's a lot of other things, like we could have taken into account like the friction within the tube, but that's not a measurable. So I did it with what we thought was measurable, and that included our volume, our period, and our pressure. So obviously with all these cases, we had a different variety of stuff, but basically with our DV, we took it as like what our error would be. So what we had it as was about 0.01 liters, which came down to like 0.1 to the -4th or whatever, -5th meters cubed. So that's obviously a tiny value. And then our period, we did, obviously with this tracker app, it's a little more accurate than we're doing it like on a stopwatch or something like that. But we can't have that come out to be like 0.003 seconds, which is fairly accurate, I suppose. And then for our pressure, the way that we just use the app and stuff, we thought it could be a little off. So we did it around 50 pascals. And I figure that's pretty close. And we can't get the exact pressure in the room rather than just the entire city of Grand Junction. So it's a little, whatever. So we came out with these uncertainties for all these different values. So obviously it ranges from about 0.007. And kappa, since it's our CP over C values, the units cancel, so it's unitless. And so there's no units associated with, we just want that ratio. So it ranges from about 0.007 all the way up to 0.03, which is all right. So we know that our desired rate is going to be that 1.4. So our only value that actually reaches that is our volume of air at 9.5. And then we're also really close with like the previous before it, but we're still a little bit short of our desired range. And that's, we kind of just chalk that up to our many possible source of air, like I was talking about earlier. And so our kappa value here, if we take into account all these and take the averages, we get like the 1.32, which is pretty good. We were told by Dr. Collins before the experiment that it's very difficult. Like most are around 1, like their kappa value is about 1, which is really bad. So I'm pretty happy with our results. And then we'll just move on to this last page. So like I said before, our average kappa value, if we take into all the different volumes of air that we had, was the 1.32 plus or minus 0.02. And like I said, the many sources of air, the air friction, the volume, the period, all that, it was a lot of possible source of error, and I'm pretty happy with how accurate we were. And obviously, like I talked about earlier, is that as our volume of air gets bigger, the more accurate our data became, and I thought that was pretty interesting. And overall, it was a pretty cool lab. Dakota was a good lab partner. We did some good work together, and I wish we could have had a little bit more time to do some more of it. But yeah, thank you guys for your time, and I'll talk to you later.